Hello there. Pen. Let's go with green today. Green pen, full screen. We are about to learn about recursive and explicit functions and the difference between them and how do we get from one to the other and all kinds of stuff like that. Typically when we talk about a recursive function, we're talking about a function that's written in some sort of form like next equals. And when we're talking about an explicit function, we're talking about one that's written in the form of y equals. Okay, recursive means how do we get the next number? So, the string of events building on what the sequence is. So, if we have a sequence of 5 and 12 and 19 and 26, first of all, what sort of sequence is it? Good, okay. And then, what's the common difference between the terms? How are we getting from one term to the next term, to the next term, to the next term? It looks like we're adding 7. Okay? And so if we were to write a next now equation, we'd write next equals now plus 7, and we'd be starting at 5. Okay? Which is a delightful thing. If I want to get the next term, I can add 7, so I'm at 33, and the one after that, I'm at 40. But what if I want to know the 100th term? I want to find the 100th term. You want to write this out the whole way through, and geez, that just seems like a recipe for disaster. So this is where the explicit function comes in handy, because we can get the 100th term if we can write this in a different form. Okay? So the explicit function works like this, y equals. And what we're doing here is we are repeatedly adding 7. Okay? So we're doing 7 plus 7 plus 7 plus 7 plus 7. And so if we wanted to, find the 100th term, we would add 7 100 times. If we wanted to find the 95th term, we'd add 7 95 times. The short way about doing that is we would just take the 7 and multiply it by whatever term we're looking for. Looking for the 50th term, x would be 50. Okay, so that's the number of times that we repeatedly add 7. And what are we repeatedly added? What are we repeatedly adding 7 to? I got it that time. What are we repeatedly adding 7 to? Well, we're repeatedly adding 7 to 5. So we've got ourselves an explicit formula. So this one is explicit because now if I want to know the 100th term, the 1000th term, the 10,000th term, I just plug it in. If I want to know the 100th term, I plug in 100. 7 times 100 plus 5, 705. I didn't have to go through and find out every term in between. Okay, so we've got the explicit, and we've got the recursive for that. Recursive. Oh my goodness. There we go. All right, so next, another one. This time we're in a table form. Okay, and we're looking at this table. These x values are going 0, 1, 2, 3, which is delightful. And so we notice that hopefully the pattern is plus 3 all the way on through, right? So if I write my recursive formula, next equals now plus 3. Starting at, it's important to have the starting at, start at 5. And so to do that same pattern with to turn it into the explicit formula, y equals, what are we repeatedly adding? 3. So instead of repeatedly adding 3, we'll just multiply by 3 however many times we need to. And then we'll add that to our starting value of 5. Okay? So the pattern maybe? Oops, so. Here's another one. What are we doing here? Oh, it doesn't look like we're doing the add thing, right? Looks like we're doing a multiplication deal. Multiply by 2. Multiply by 2. Multiply by 2. And we know how to write a next now equation for that. So we spent a little time in the last video doing that. Next equals now times 2. Start at 5. And so this time our equation, our explicit equation, is going to take a different form. It's still going to be y equals. All right? But to get to the 100th term, what we would do is we would multiply by 2, 100 times. Sometimes 2, by one time gets me the first term, 2 times gets me the second term, 3 times gets me the fourth term. So repeatedly multiplying takes the form of an exponent. So I'm taking 2 and I'm multiplying it by itself however many times I want. I want to get to the 5th term, I multiply 2 by itself 5 times. I want to get to the 50th term, I multiply 2 by itself 50 times. And then the only thing we've got to do is once we get this, how many times we're doubling, is, well, what did we start off doubling? And what we started off doubling was the 5. So we rewrite this as 5 times 2 to the x. Okay, and that is my explicit equation. If I wanted to know what the 50th term was, I could happily get that. I would just have to plug in 50, 2 to the 50th, figure out what that is. Pretty big number, so we probably have to use scientific notation, and then multiply that by 5. Is that right? All right. So what's going on here? Oh, looks like we're doing a little subtraction, maybe? Subtraction. Subtracting 7. Subtracting 7. No big deal. Okay, next. Equals. Now, minus 7. I'm going quick because I think you've got it. If you don't, if you aren't quite there, then probably slow down and stop and figure out, like, oh, what is he doing? Or ask the questions. Next equals now minus 7. Start at 15. That's the next now. That's my recursive equation, my explicit equation. Going to follow that same format. Y equals. I'm going to repeatedly subtract 7. So I'm going to do subtract 7 however many times, and I'm starting at 15. There's my y equals equation. Okay, started at 15, kept subtracting 7. Want to know the 100th term? Negative 7 times 100, add 15 to it. Okay? All right, so what's going on here? It looks like we're multiplying by, well, I don't even know. So I'm going to go 80 over 100, figure out what that is. Do 64 over 80. If we're not sure, if we can't just look at it, then we do that. 51.2 over 100. So it turns out 80 over 100 is 0.8. 64 divided by 80 is 0.8. So in this particular geometric sequence that we have here, geometric sequence, because we're multiplying, it's poorly written geometric, but you can figure it out. That geometric sequence, our constant multiplier, our ratio, is 0.8. So if I were to write a next now equation, it would look something like next equals, better if this is held there, next equals now times 0.8, and we start at 100. So to write the explicit formula, I'm going to go with my thing that I'm repeatedly multiplying by. I'm repeatedly multiplying by 0.8. I'm going to raise that to the x power. And then the thing that I'm starting at, 100. So I'm going to take 100 and I'm just going to repeatedly multiply it by 0.8 until I get where I want to be. Okay? I don't want to have to go through and do this a bunch of times. So just for instance, like I went, I don't know if I did the 50th power. I'm going to just grab the calculator. See it right there. If I hold it up in front, well, let's just see what happens. So I do 100 times 0.8. I have a calculator on here I should use. And I'm going to do it to the 50th power. Okay, can you see that? It's in front of my face. 100.8 to the 50th power. So I get that particular number there, which is what? 0.00142 I'm going to go with for right now. So when x equals 50, y equals 0.00142. And we remember that that scientific notation is 1.42 times 10 to the negative third, just to do a little wraparound on that one. Okay? Generally speaking, for a linear equation, our next equals now, our recursive pattern is now plus some number starting at some other number. And when we turn that into an explicit equation, we would have y equals mx plus b. You ever seen that before? Good. Yes, we've seen that before. Okay, now plus whatever the number is, and then turns it into that y equals mx plus b form that is sort of a general form for a linear equation. If we have an exponential model, then that we get a next now equation, a recursive equation now times b starting at a, and the general form is y equals a times b to the x. Okay, so what started out as an arithmetic sequence turns into a linear pattern. What started out as a geometric sequence, we say has an exponential pattern. Exponential means it grows proportional to itself. Linear means it grows at a constant rate. So that's sort of the pattern that we look for. Let's see, what do we have next? A word of caution. remember from the last video that look at this one. It doesn't start at 1, or it does start at 1. Doesn't start at 0. So we always have to go back to that 0th term. Let's just look. We're adding 3. We're adding 3. We're adding 3. So we know it's a linear sort of linear concept. It's an arithmetic sequence. My next equation next equals now plus 3. And here's this cautionary part. Start at. We got to go back to the 0th term, so when x is 0, we go back 3 more, y was equal to 2. So we start at 2, and this turns into y equals 3x plus 2. Okay? Went a little fast on that one, but I think you've seen that caution before. And what do we have left? Oh, the U-turn. So you ought to be able to start with the explicit form and turn it into the recursive form. Okay, so we ought to be able to go backwards, and if you just look at this 2 slides back, the pattern, okay, if I start with mx plus b, I should turn it into now equals now plus m starting at b. So it's going to turn out to be next equals now plus 2 start at -4. Okay, this one's going to follow the pattern of a times b to the x. So going back there, it's going to be now times my base, starting at my a value. So it's going to be next equals now times 5, start at 4. Okay? So recursive to explicit, we ought to be able to be familiar to be able to get back and forth. Next now equations are really nice if you're looking for the 4th and 5th term, but when we're trying to get to the 50th term, even the 10th term, God, I'm lazy, I would stop it. If I got to go much beyond 10, I would probably say, I need an easier way to do this. And it's, hopefully mistake-free. So we've got linear models, we've got exponential models, we've got arithmetic sequences, we've got geometric sequences. They're all related to each other. I think that's the end. That is about it. So thanks for watching. Hope you learned something. If you have any questions, feel free to let me know. We'll talk to you soon.